Hello everyone, we have discussed a capillary rise in different capillary tubes with different radius. We have discussed the rise of capillary in capillary tubes of different radii. We have seen that if you have a capillary of diameter as small as the clay pore size, equivalent to the clay pore size, then the capillary rise would be too much, too high value, as high as 2910 meters, so nearly 3 kilometers. So for clay particles, usually they are plate like structures. If you assume that this is the plate, this is one plate, and you have another plate, so when they are immersed, in water, so what is the rise of height one can find out? So you would see that the water forms a capillary, forms a curvature with the surface, and it should rise up. So what is the rise we can find out, because we know the force due to surface tension, the force due to surface tension is Ts times the total length. So total length, if you consider length of the particle as small l, so the water can interact with the surfaces at two interfaces along L plus L 2L. So this is the total force due to surface tension, so which should be balanced by the weight of the column when it raises. So the weight of the column should be equals to the density of water times G times the volume. So this should be in kilonewtons, kilonewton per meter cube. This whole thing is kilonewton per meter cube, into meter cube should be kilonewton, so that is the weight. So this should be density of water can be found, and volume is, if the rise of height is say h, and distance between the particles is small d, so then it should be volume is height times L times d. This is 2s into, this is 2s times 2L. So when you simplify, you get an expression for h equals to 2Ts by rho W into G times D. So this is the expression one can use for estimating the capillary rise. Here the surface tension we can find out depending on the temperature. At different temperatures we know the surface tension. The rho W density of water is also known at a given temperature. G is 9.81. We can substitute R. Together we can substitute the unit weight of water, which is 10 kilonewton per meter cube at standard temperature, and D is the space. Generally the particle size or particle thickness would be, the clay particle thickness would be as small as 1 nanometer to little coarser ones maybe 10 nanometers. Distance between the particles may be as high as maybe 100 to 1000 nanometers or even slightly more. So if you substitute, you can approximately calculate what could be the rays of height. So this could be in meters. So but then we need to assume that the particles have stacked up. Each particle stacks up like this, and another particle stacks up like this, and which forms a cavity, or which forms a small pore, which forms a pore, and then water should raise up. This is the most unlikely. Rather than that, if you assume that the particles are stacked like this, these are clay particles which are stacked, and it forms a tactoid kind of thing, then this pore size could be approximated as a spherical, and we can use the earlier expression to find out the earlier expression, that is height is equals to 2Ts by simply r. We can assume that the radius of pore size could be related to the particle size, or pore size could be estimated from different means, and if you substitute, you can approximately estimate what is a capillary rays. So there are various ways researchers have estimated this by relating the pore radius to D10 different particles, D10, etc. We have seen that if you insert a capillary tube in a beaker of water, a capillary tube made up of a glass tube, we have seen that there is a rays of water raises and forms meniscus like this. We have discussed earlier that this raise is because there is an adhesive force between the water molecules and the glass surface. Because of these adhesive forces, water tries to creep, and then it tries to occupy the maximum possible surface with a thin film. So in turn, as there are cohesive forces between the molecules, the water molecules get pulled up and it forms a meniscus like this. This is what we have seen. So therefore, apart from the radius of the capillary tube, the adhesive force between the water molecules and the solid surface wall, that also plays an important role in governing the capillary rays. Such adhesive forces are quantified using contact angles. If the adhesive force between liquid and solid or capillary surface are weaker than the cohesive force between the individual water molecules withdrawn from the surface of the wall. So this retraction makes the surface to curve, because if this is in this you are immersing a capillary, the forces between the adhesive force between the water molecules and the glass surface or the surface of the solid are weaker than the cohesive force between the individual water molecules, then water withdraws from the surface and it retracts, and which forms a concave surface. It forms a convex surface like this. So it forms a concave in the liquid phase. So when the concave surface forms, so the pressure within the concave side would be higher. We have seen that the pressure in the concave side would be higher than the pressure on the convex side. So therefore, the liquid surface depresses in the capillary tube in order to compensate the increase in the pressure. So if you take a capillary, I'll redraw it. If I take a capillary, this is the surface of the fluid in the container, and when water retracts, it forms a meniscus, and this meniscus concave in the liquid phase means that the pressure in the liquid is higher. So when the pressure in the liquid is higher, to balance this, so there should be a depression. The water should start collapsing. The water, the capillary would start depressing or collapsing within this capillary tube. So at equilibrium you would see that there is a depression of this fluid within the capillary tube you would see. So best example is mercury in a glass tube. Mercury, you use mercury as liquid and use a glass tube, then it will depress. This could be better quantified using contact angle. If I magnify this capillary tube and this is the meniscus and the interaction that takes place with the solid, and this is the contact angle. Essentially the contact angle is a measure of angle between line tangent to the gas and liquid interface. The gas and liquid interface is this, and line defined by liquid and solid boundary and is measured within liquid. So this is contact angle theta. So similarly here the contact angle would be, this is in water, this is water as liquid and a glass tube as solid. So the theta is less than 90. In case if you take mercury, if I magnify this, this is the capillary and this is the surface, water surface, air water interface. So here the contact angle would be this. So here mercury as liquid, mercury used as liquid, and glass tube is a solid surface, and theta would be more than 90 degrees. Theta would be more than 90 degrees. So therefore liquid surface interacts with the solid with some angle known as contact angle theta. So the nature of the meniscus, curvature meniscus, whether it's a concave or convex, indicates the fluid is wetting or not, or repelling fluid. So the fluid kind of repels from the surface in this particular case, so therefore it convexes up like this, or concave in the liquid phase. So at equilibrium, let us consider the capillary tube again, and you have the meniscus, and this is the meniscus, and you have a contact angle theta. The radius of the curvature is capital R, and this will be same here. This is capital R. The radius of the capillary tube, radius of the capillary tube is R, then this is D is equals to 2R. So here this is a normal to this line, this tangent. Here this line is perpendicular to this tangent, and if I draw a line, if I draw a radius, this is again tangent perpendicular to the wall. So therefore this angle again should be theta. So essentially if I again magnify this, this is capital R and this is the wall, and this is small r, this angle again should be theta. So r cos theta would be equals to small r. So earlier we have derived a Laplace equation According to the Laplace equation, the pressure drop across a air water interface U A minus UW is equals to 2 Ts by R. R is the radius of curvature. So if we substitute R from here, this would be R into cos theta. This is the same expression again we have derived for rays of capillary tube. So here U minus UW, that could be written as H times gamma W, then this would be 2 Ts cos theta by R gamma W, because in order to maintain the hydrostatic equilibrium, the induced pressure U minus UW should be balanced by the rays of capillary. So therefore H is equals to U minus UW divided by gamma W. Here H is positive if theta is less than 90 degrees. Theta H is negative if theta is more than 90 degrees. So that means there is a depression. This can be directly understood. What is the capillary raise or capillary depression that takes place if contact angle is changing? So the contact angle is very useful to quantify whether there is a depression that is taking place or there is a capillary raise that is taking place. There are several possibilities for the contact angle. The pressure drop across the interface in a capillary tube for any contact angle could be estimated using this particular expression, and the possibilities here are probably 1, theta is equals to 0, contact angle is 0 degrees, means perfectly wetting. It's a perfectly wetting. So in that particular case, the small r is equals to capital R, because cos theta is equals to 1. So second possibility is that the contact angle vary between 0 and 90 degrees. This is partially wetting. So partially wetting surface, this is a typical value we see in soils. So in this particular case, the UA minus UW is positive, so UA is more than UW. So the third possibility is that theta is equals to 90 degrees. If there is 90 degrees, so then it's a perfectly flat surface. So R equals to infinity, or UA minus UW is UA is equals to UW. So you have a perfectly flat surface. So here you have flat surface like this. So when you have a very large capillary, then you will have UA is equals to UW, because cos theta is 0. So you get UA minus UA is equals to UW, or UA minus UW is equals to 0. So when you have theta between 90 and 180, that is capillary depression that takes place. Here this is the angle. So this one is this one causes capillary depression. The pore water pressure, the UW, would be more than the atmospheric pressure. So that is a typical case in mercury, and some of the organophilic soils would exhibit this kind of a behavior. And if theta is perfectly 180 degrees, so it is a perfectly repellent material. So these 5 possibilities could be there, could be considered for our soils. This is more relevant. Theta varies generally between 0 and 90 degrees. Slowly we are inching towards understanding important state variables in unsaturated soil mechanics. So one of the important state variable in unsaturated soil mechanics is this quantity UA minus UW, So this is the pressure drop across the water interface, that's what we have understood. And this one we call suction very soon. We introduce as suction this quantity very soon. And once we understand this suction concept, then we bring in important constitutive relationships relationship in unsaturated soil mechanics, such as soil water characteristic curve. So before understanding, let us try to understand the equation for the pressure drop in case if you have a non-spherical curved surfaces. So this is one particular case where the diagram shows there's a curved surface, a small area delta A, a small surface with area A, a curved surface which has two different curvatures. One is R1, another one is R2. Here this is R1 and this is R2. Two different curvatures you have. So you can imagine this as a balloon, which is one small part of it is considered and which has the curvatures in two different directions, R1 and R2. And when it is blown, giving extra energy or extra pressure, this would assume this by changing its area from A to A plus delta A. So in this particular case, we can estimate what is a pressure drop across the interface by analyzing what is the work required, work done for expanding this one, this area to this. Let us try to understand. So based on the work needed to increase the interface area by infinitesimal amount delta A, so the work required, work done is dW is equals to Ts surface tension times the change in area. So surface tension has units of Newton meter or millinewton per meter, and this has units of meter square. So therefore the multiplication of these two would result in work, it's either joule or Newton meter. So you can estimate what is a small area. So small area or change in area is nothing but x plus delta x, sorry I am using capital X, x plus delta x times y plus delta y minus x times y. So this is the change in area from this segment to this segment. So this is nothing but x delta y plus y delta x plus xy, that gets cancelled, and you will get plus delta x delta y, that is too small, the second order term you can ignore. Then this is the, because there is an infinitesimal area that is increasing due to small work that is done, due to the work that is done. So this is the change in area. So this causes a pressure change across the interface. That pressure change is again dW is equals to the pressure change you can estimate, that is dP times x times y. So that is the area. So pressure times area, that is a force times the movement. This is a small move. This has element has moved from here to here while expanding. So this is a delta z, work done for force, work done for moving this delta z, increment delta z. Then this is work. So work done is equals to delta p times xy is the area times the delta z is the distance between these two segments. So here caution, these are xy and this is into. So here this can be simplified. If this segment is considered like this, so this is the one triangle, this is formed with this. So this is the bigger triangle. So from the property of triangle, this arc length is equals to r times the theta. From that triangle property of the similarity of the triangles, one can obtain the y plus delta y divided by the y is equals to r1 plus delta z divided by R1. Similarly, you can consider other triangle from this. This is another triangle R2, and similarly you can also obtain x plus delta x by x is equals to R2 plus delta z by R2. So this is 1 plus delta y by y is equals to 1 plus delta z by R1. So therefore delta y is, so the delta y, therefore the delta y is equals to the y times delta z divided by R1, and delta x is equals to x times delta z by R2. So when you substitute this in the area and write the work done, then this is equals to the Ts times, this is Ts times 1 over R1 plus 1 over R2, and xy terms you can bring them out, and delta z term you have, and when you equate this to the work done due to the pressure drop, there is a delta P times xy times delta z. So then delta z xy get cancelled, so therefore the change in pressure or pressure drop across the interface is equals to Ts times 1 by R1 plus 1 by R2. So this is the expression. Here delta P is UA, this is the delta P is, here the delta P is UA minus UW. So there is a pressure drop across the interface. So this is the expression you get. This is the Young-Laplace equation. So this Laplace equation could be, Young-Laplace equation could be applied for understanding the soil behavior. So when you have two soil grains which are located, so one in here, so another one is here. So this is water. So there is a liquid bridge that forms, there is a meniscus that forms, that is like this. So with a curvature, with a radius of curvature R1, with the radius of curvature small r1, there is a interface that forms. So this radius of curvature changes in this direction. So if you consider a plane along this plane, this appears as if it's a horse saddle, the radius that changes in along this plane. So that is along this one is R2. So it seems in this particular case the R2 is convex and R1 is concave. So in that particular case the liquid bridge, the pressure drop across a liquid bridge in this particular case would be UA minus UW is equals to Ts times 1 by R1, which is equal to capital R1 in the Young's Laplace equation, plus 1 by minus R2. Earlier in the Young's Laplace equation, both R1 and R2 both are concave, but in this case the R2, which is a liquid cylinder that is available here in the liquid bridge, is a convex, so it should be minus R2. Then this equation turns out to be Ts times 1 by R1 minus 1 by R2. So this is the expression for liquid bridge in soils, and this is the pressure drop because of that. So when the soil grains, when they come close to each other, because when water tries to evaporate, when the water is lost between the soil grains, so these particles would try to move close to each other. When the distance between these two grains decrease, So the R1, R2 also change accordingly, then the pressure drop across the interface would change. That could be estimated using this particular expression. So far we have seen that when you have a capillary, or when you have a curved interface, what is the pressure drop across the interface we have seen. And after that, when you have a capillary rays, in a capillary tube, then we have seen what is a pressure drop, which is again dependent on it depends on not only the capillary tube diameter, it also depends on the contact angle. So in case of two solid grains, which are because of which there is a liquid bridge that is forming between these two grains, then this is the expression we have seen. This could be possibly applied for understanding the soil behavior, unsaturated soil behavior. One more important concept in physical chemistry that is directly applicable for our soil mechanics is a Kelvin's equation, or vapor pressure lowering. This is very important concept for even to estimate one of the important state variables of unsaturated soils, such as total suction estimation. So according to the Kelvin's equation, as we have seen earlier, that the vapor pressure of liquid depends on temperature. As temperature increases, the vapor pressure increases, and also on presence of solute in solvent or presence of salts in water. So because of the presence of salts in water, the vapor pressure decreases. And also there is an important parameter, that is important state variable, that is pressure. So applied pressure on the liquid also influences the vapor pressure. Further, we have seen that curvature at air water interface that gives rise to this is convex. So the curvature at the air water interface gives rise to a pressure drop across the interface. Therefore, vapor pressure above the curved surface would be expected to be different from the vapor pressure above the free surface, flat surface. So this is an important point. So that because there is a pressure drop across a curved surface, the vapor pressure would be different, because vapor pressure depends on the pressure applied on the liquid. So therefore, Kelvin's equation relates this change in the vapor pressure with the curvature or the capillary tube radius, etc. Capillary tube radius or curvature, these two things could be related using Kelvin's equation. So UV is the vapor pressure, and this is the vapor pressure near the flat surface or with the saturated solution. Vapor pressure UV naught is a vapor pressure at equilibrium when it is interacting with a flat surface, and exponential of Vm is a partial molar volume of water vapor, which has units of meter cube per mole, and delta P is change in pressure or pressure drop across the interface divided by RT. R is gas constant, T is temperature in Kelvin. So the delta P here could be estimated from different equations so far we have discussed. Could be from Laplace expression, which is delta P is equals to 2Ts by R. Laplace expression when you use it for curved surfaces, or it could be for Young-Laplace equation when it is non-spherical curved surfaces. So then it would be Ts times 1 by R1 plus 1 by R2. So this is a Young-Laplace expression. If this becomes spherical, that means R1 and R2 both are one and the same, then this boils down to the Laplace expression 2Ts by R. So this is Ts into 1 plus R1 plus R2. Or if you are assuming a toroidal approximation, if you are using toroidal approximation for understanding the unsaturated soil behavior, then this could be Ts times 1 by R1 minus 1 by R2. So anything, the pressure drop using different expressions could be obtained, and if you substitute, you would understand what is the change in the vapor pressure. So this can be simplified as UM minus UW is equals to minus RT by VM times log UV by UV naught. So for one particular case, when R1 is 10 power minus 7 meters and R2 is 10 power minus 4 meters. So in this particular case, you can estimate what is the pressure drop, that is Ts into 1 by R1 minus 1 by R2 using toroidal approximation. This is here, this is 722.75 millinewton per meter at standard temperature, and if you substitute R1 and R2, you would get the value is equal to 726.8 kilopascal. This is a pressure drop. So you can estimate for this particular pressure, this is the pressure we estimated, and for this particular pressure drop, what could be the vapor pressure above the surface, above that curvature, one can estimate. So here you can substitute this value. So this is 726.8 kilopascal is equals to minus R is 8.314 joule per Kelvin mole times 298 Kelvin divided by Vm is partial molar volume of water vapor, which is 18 kg per molecular mass is kg per kilomole. So the molecular mass is 18 kg per kilomole, which can be written in terms of volume. So therefore 18 times, this could be 10 power 3 centimeter cube per kilo 10 power 3 mole. If you write in terms of meter cube, this is 18 times 10 power minus 6 meter cube per mole. So you can substitute 18 times 10 power minus 6 meter cube per mole into log, this is nothing but RH, right? So UV by UV naught or UV sat is RH. So therefore RH is, if you simplify here, joule can be written as Newton meter. So here kilopascal can be written as kilonewton per meter square, and after simplification the Kelvin gets cancelled, and here you have meter cube per mole, the mole gets cancelled here. Here Newton meter, you get Newton per meter square. So here you have kilonewton per meter square. When you simplify, you multiply with 10 power 3, then you get Newton per meter square. Then when you simplify this, you get 0.9947 is the RH, or 99.47%. So at standard temperature, the RH UV sat, saturated vapor pressure, is 3.167. So therefore UV could be 0.9947 times 3.167 kilopascal, which is equals to 3.15 kilopascal. So this is how the vapor pressure above the curved surface can be estimated. So we use this particular technique to measure the vapor pressure above the curved surface. From that we obtain what is a UM-UW, or pressure drop across the interface. So for estimating the one of the state variables, that is suction or UM-UW, we measure the UV and we estimate this particular value using Kelvin's equation. Thank you.